Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 40th lecture. In this lecture, we will be discussing clock tree synthesis. In the earlier lectures, we had seen that the physical design is broken into multiple tasks which are shown in this figure. And in earlier lectures, we had looked into chip planning and placement. So, in this lecture, we will be discussing the next step in the physical design, that is clock tree synthesis, right. So, specifically in this lecture, we will be first looking at some terminologies related to clock tree synthesis, then we will be looking at various types of clock distribution networks, and then we will be looking at clock network architectures and a concept of useful skews. So, before going into physical design, we had done logic synthesis, and in logic synthesis we assume that the clock signals are ideal. Now, what do we mean by ideal clock signals? So, by an ideal clock signal, we mean that the clock signal has the same waveform at all points in the circuit. By waveform, we means that the value of the voltage of the clock signal at various time instant. So, ideally we expect that if there is a clock source and it is generating a clock signal, the exact clock signal is available at all the sinks or all the clock pins of the flip flops at instantaneously, right, and at all the points in the of the circuit, the clock signal is behaving in the same manner, right. So, in particular we expect that there is no clock skew, and what do we mean by clock skew? The clock skew is the difference in the arrival time of the clock signal at the flip flops. So, if there is a clock source, so this is a clock source and there are multiple clock pins in our design, right, we expect that at all the clock pins in the design, the clock signal is being received simultaneously at the same time, right. So, it means that there is no skew or difference in the arrival time meaning that how much time it takes from the for the clock signal from the to start from the source and reach the clock pin, right, that is the arrival time, right. So, the arrival time, we expect that the arrival time at all the flip flops of our design is the same, right. Now, this is the ideal behavior, and if we go into physical design, the ideal behavior can never be ensured. Why it can never be ensured? Because we are making the layout, and in the layout the clock signal will be generated from one particular point, maybe say from a clock generator, and from there it will be fed to all the clock flip flops in our design, right. Now, as the clock signal goes from one point to the other, or it propagates through the network of network of various components in the clock network, the clock signal will encounter delays, and these delays can be different for different clock pins, right. So, for some clock pin the clock signal can reach very quickly, for other it may take more time because the distance between the clock source and that pin is more, and so on, right. And therefore, in physical design we cannot ensure we can have non-idealities because of the delays in the clock path. Now, what does the clock tree synthesis try to do? So, clock tree synthesis tries to make or implement a clock distribution structure such that it mimics an ideal clock, or the layout of the clock components are made in the clock network such that the behavior of the clock signal is similar to the ideal clock, meaning that the ideal clock is the one which we want, right, that is what is targeted. But due to no delay effects in the clock network, that can never be ensure that a clock network can never be implemented that such that the clock is ideal, meaning that there is no skew. But nevertheless, clock clock distribution, clock tree synthesis tries to ensure is that the clock skew is minimized, right. So, it tries to build a clocking structure such that the ideal clock network is mimicked, right. It can never achieve the full ideality, but it tries to achieve a zero skew or non or similar to an ideal clock, right. So, it minimizes the clock skew and it inserts clock buffers, inverters and performs routing of the clock distribution network. Now, the clock tree synthesis also tries to reduce power dissipation in the clocking structure. And why does it do it? Because the clock network consumes significant portion of the active power. It can be as high as 25% to 70%, right. And therefore, the CTS or clock tree synthesis tries to reduce the power dissipation in the clocking structures. So, the clock signal is a very active signal, meaning that it transitions in one clock cycle, it transitions one rising and one edge, one falling edge it will have, right. So, the clock signal transitions very rapidly and therefore, dynamic power dissipation in clock network is very high and therefore, CTS tries to reduce the dynamic power dissipation in the clock network. And then it also tries to fix timing violations and signal integrity issues, because the clock signal is a signal which is rising very rapidly, right. Ideally, its rise transition should be as abrupt as possible, right. Now, because the rise time is very small or the signal is clock signal is transitioning very quickly, it can impact neighboring lines, right. And therefore, the signal integrity issues related to clock signals are also important in CTS. Now, let us look at a few terminologies related to CTS. So, what is a source? So, source for a clock is the starting point of the clock signal, and what are sinks? Sinks are the final receiving endpoints of the clock signal. For example, if we look into this structure, so here there are these flip flops, right, and these are being clocked by this clock generator, right. So, the clock generator is basically generating the clock signal, and therefore, this pin of the clock generator can be considered as the clock source, right. Typically, the information of the clock source is obtained through the SDC file. So, remember that when we discuss constraints, we discussed that how sources of the clock sources are defined in the SDC file using create clock and create generated clock constructs. So, those information are used by the tools to infer that what are the clock sources in our design. And these are flip flops, and the pins, the clock pins of these flip flops, these are the sinks of the clock network. Now, in the clock network, there is a tree kind of structure. If we look into the clock generator, right, the clock generator is the root of the tree, and from there we have various branches emanating, and finally, the clock pins, those are the leaves of the tree, right. So, we can think of that the clock source is the root, from there the branches emanate, right, and then finally, the endpoints are the clock sinks, right. And in the branches, what do we have? We will have many buffers and inverters. So, these are buffers, there could be inverters and so on, right, which are basically used in the clock network to deliver the clock signal, right. Now, let us understand or a very basic question, that why do we have so many buffers and inverters in the clock network? What is the role of these buffers and inverters? So, to understand it, let us take an example where, say, there is an inverter, right, and this inverter is driving a very long wire, right, and at the end there is another inverter, right. Now, this wire is long. Now, why we are taking a long wire? Because in the clock distribution network, from the source to the sink, you have a long path, right. The flip flops can be on the layout at any point, right, and therefore, there will be long paths from the clock source to the sinks, right. Now, let us assume that the length of this this wire is say 2L, right, 2L, right, and let us assume that the resistance per unit length is R and capacitance per unit length is a small c, right. So, what will be the resistance and the capacitance of this wire? The resistance R can be given as R, small r, resistance per unit length into 2L, right. So, we can write 2RL, right, that is the resistance, and what is the capacitance? Again 2CL, C is the capacitance per unit length and 2L is the length, total length of this wire, right. Now, as a first approximation, what will be the delay of this interconnect? We can think of this delay as a first approximation as a product of R and C, right. And therefore, if we take the product of these two terms, it will be 4 RC L square, right. Now, let us take that, assume that we have divided this wire into two parts, take L driven by one side and L on the other side. So, suppose we have the same structure and in this we insert a buffer at the length of L, and then another on the other side we are left with L. So, we have just transformed this circuit into another circuit in which the length is, so we have extra buffer here, right. Now, let the resistance per unit length and capacitance per unit length be the same, right. Now, in this case what will be the delay that we expect? The delay that we expect in this case will be tau approximately RC L square for the first section plus the delay of this buffer, right, let us call it B, plus the delay of the second section, that is RC L square, right. Now, if we assume that the buffer delay is very small, compared to the wire delay, we can neglect this term, right, and the total delay in this second circuit will be approximately 2 times RC L square, right, 2 times RC L square. Now, if we compare with the original circuit, it has reduced by half, right. So, if there is a long wire and if we insert a buffer in the middle, then the total interconnect delay is expected to reduce, right, if given that the delay of the buffer itself is small, right. So, that is the first reason why we want to insert buffers in the clock network, because there are long wires and to reduce the delay we add buffers at different, or we divide the long wires into smaller wires and have buffers in between, right. The second reason is that if there is a long wire and the signal starts an ideal clock signal which is rising very quickly, right, transition time is very small, when it reaches the end point, the signal quality will be very bad, meaning that it will be rising very slowly, right, because of high resistance and capacitance offered by the interconnect, right. So, the slew in this case may be say 2 picosecond, here the slew will increase to say 100 picosecond, right, and this is very large, right. So, we want the clock signal to be very sharp. Now, if we introduce a buffer in the middle as in the second circuit, what we are doing is that in a sense these buffers will have VDD also and ground line also. So, this buffer is basically pulling up the signal to make it more sharper, and as a result the quality of the signal that finally reaches this end point, this buffer, the final buffer here, that improves. So, if the signal was very sharp here we expect that it will be the signal quality will be much better because of the driving effect of this buffer, right. And that is why we have in the clock tree we have lots of buffers and inverters to restore the quality of the clock signal and also reduce the delay of the clock signal in propagating through the clock network, right. Now, what is insertion delay in a clock tree? It is the time taken by the clock signal to propagate through a clock tree and reach the clock signal, right, clock sync, right. How much it takes, the time taken for a signal to go from the clock source to the clock sync, that is known as insertion delay. Typically, we call this as latency during synthesis, but when we go to clock tree synthesis, we get actual value, and there we call it as insertion delay. Latency is a kind of an estimate of the insertion delay. Now, what is clock skew between two sinks? Clock skew is the difference in the arrival time of the clock signal between a pair of sinks S1 and S2, right. If there are two sinks S1 and S2, if the difference in the arrival time of the clock signal is known as clock skew, right. So, mathematically delta S1 S2, that is the skew between two sinks S1 and S2 is equal to T S1 minus T S2. T S1 is the arrival time of the clock signal at S1 and T S2 is the arrival time of the clock signal at S2. So, if we look into this clock tree or that we discussed in the last slide, if say that the clock signal was starting at a 0 point and the delay of insertion delay was say 30 picosecond, then the arrival time at A will be 30 picosecond, right. Similarly, 40 is the arrival time at B, C is the 30 is the arrival time at C, and 26 is the arrival time at D. So, assume that this is in this circuit. Then in this case, what is delta AB? That is the skew between the sink A, this clock pin, and sink B, this clock pin. This will be equal to 30. Let us assume that the time unit is picosecond. So, the delta AB will be 30 minus 40 is equal to minus 10 picosecond, right. Now, if we take delta BA, then it will be 40 minus 30 is equal to 10 picosecond, right. So, the sign of the skew is also to be noted. Now, what is global clock skew? So, global clock skew is the maximum value of the clock skew between any pair of sinks. Now, if there are say four clock sinks in this case, then what will be the maximum clock skew, right? That will be that is defined as the global clock skew, right. So, if we take the maximum value of the clock delta S1, S2, where S1 and S2 are any sinks, then that we get the global clock skew. So, in this case we see that this one is having the if we take the difference between B, right, and D, right, then we will get the maximum, right. So, because D is having the minimum arrival time and B is having the maximum arrival time. So, in this case delta global is equal to 40 minus 26 is equal to 14 picosecond, right. So, these are some of the definitions you should be aware of, and typically the tool tries to CTS tool tries to reduce the clock skews between flip flops, right. And sometimes for easy evaluation, the clock tree synthesis tool can also target improving the global clock skew rather than looking at individual clock skew between two sinks. Now, let us look into that how clock distribution networks are created. So, we create clock distribution network in two steps or in two hierarchies, right. So, at the top we have what is known as global clock distribution network, and using this global clock distribution network we drive local clock distribution network. So, what it means is that suppose we have a chip, right, we have a chip and we have a clock source. So, from this clock source we will first make a global clock distribution network, right, which will basically distribute the clock signal throughout our chip, right. And wherever this global clock distribution network ends, right, these are the endpoints of the global clock distribution network. I am not showing the buffers and inverters in this global clock distribution network just for easy illustration, right. So, from the point where the global clock distribution network ends, there the local clock distribution network will start, and these this local clock distribution network will basically supply clock signals to the flip flops, right. So, the responsibility of global clock distribution network is to distribute or propagate clock throughout the chip, right. Now, from the endpoints of the global clock distribution network, the local clock distribution network starts, and those local clock distribution network delivers the clock signal to individual flip flops. Okay. So, let us see the differences between these two networks. So, global clock distribution network distributes clock to various parts of the chip and over larger area, while local clock distribution network distributes clock to smaller parts of the circuits. And global clock distribution network will have larger buffers and it will be numerous, right. Why? Because the global clock distribution network needs to propagate clock signal to over a longer length, and therefore will need more buffers and larger buffers, right. And the global clock distribution network will consume larger power because of larger buffers and also the larger capacitances associated with the global clock distribution network. And another point to note is that the top level clock distribution network or the global clock distribution network needs to be planned, and lot of manual intervention is made in the designing of global clock distribution network, while automated clock distribution network while the local clock distribution network, those are created automatically by the CTS tool, right. So, now let us look into that how the global clock distribution network is created. So, typically we create global clock distribution network in a symmetric manner, or in a symmetric tree form is one of the ways in which we can implement global clock distribution network. So, in symmetric tree architecture, what is done is that the clock is first routed to a central point in the chip, right. From the clock source, the clock is first routed to the center point in the chip, and from central point another symmetric architecture forks out. So, there can be many types, for example, H tree type or X tree type of symmetric tree architecture is very popular. So, let us understand what is H tree or X tree architecture. So, this is an example or this is a figure of H tree architecture. So, this is the clock source, from here the clock signal goes and first routed to the center of the central point in the chip, right. And from the central point we have another symmetric structure, that is H, right. And then wherever the end is there of H, we have another symmetric structure and so on, right. Similarly, we can have an X type of architecture, right. So, what we have from the clock source, first we route it to the center point of the chip, right. Then from the center point we have a symmetric X architecture, right, and where this X end, there we have another symmetric architecture, right, and so on. So, if we look into this architecture, then we can these both architecture, we can see that from the clock source to any of these endpoints, these all are endpoints, right. These endpoints all have the same wire length, right, same length, right, and therefore, we expect that the clock signal will encounter exactly the same delay in all the paths, right, because the endpoints, all the endpoints have the same distance from the clock source, right. So, ideally if each path is balanced, skew will be 0, right. Ideally that will be the case. We will of course will add buffers and inverters in this network to enhance the drive strength and restore the quality of clock signal. And if we add matched buffers and inverters, then ideally the clock skew will be 0 at each of the endpoints in our clock distribution network, right. However, due to PVT variations, skew will still be observed, right. For example, when we fabricate it, there can be small differences in, say, the thickness of the wire, right, because of unavoidable process induced variations, right. So, even though we have designed the length to be exactly same, the capacitances can vary for different sections of the interconnects, and even if we have matched in buffers, some buffer can have more delay, some can have less delay and so on, maybe because of the variation in the gate oxide thickness and so on. And as a result, what can happen is that the delay at different endpoints may be slightly varying, right. At, for example, here we have, say, a delay of, say, 10 picosecond, and at this point we have, say, 8 picosecond and so on, right. So, just for an illustrative purpose, do not take it as exact numbers, right. So, this is so due to PVT variation, the skew will still be observed in this kind of architecture, right. Now, how to reduce even that skew, right, even in the, if that are observed in symmetric architecture. So, one of the solution which is widely used is to use non-tree architecture, right. So, even though we call it as clock tree synthesis, many a times the clock distribution network is not a tree, it is different architecture. So, we instead of a purely tree architecture, we can have a non-tree architecture which can reduce the PVT variations. Now, what can be this non-tree architecture? A simplest case can be that we have cross links between nodes. For example, between these two nodes, right, if we ignore this cross link, then the distance from this clock source to the end points all are same, and therefore, ideally the skew should be 0. But because of PVT variations, there can still be skew, but if we introduce cross links as it is shown between two points, then the delay at this point and, say, delay at this point, those will be correlated. Why? Because of the cross links, they are sharing some paths, right, and therefore, if the path between at the two endpoints path is being shared, right, then the delay will be correlated, and that is what will be observed in these two cases. And as a result of that, the PVT, the impact due to PVT variations is expected to be lower in this architecture compared to a purely tree architecture. Now, we can take the concept of cross link further up. What we can do is that instead of tree with cross link, we can make a mesh architecture, which is where there are cross links everywhere, right. So, what we do is that we create 2D structure with redundant wires and devices, right. So, we create first a mesh architecture over the entire chip area, right. Over the entire chip area, we create a mesh architecture, something like this, and drive this mesh architecture from the clock source at multiple points. So, we have shown only, say, 1, 2, 3, 4, 5 points. There could be clock source can be driven from this side and so on also, right. So, we can drive it from multiple points, right, and if we look into any one point in this grid, there will be multiple paths from the clock source to this point through the mesh, right. Similarly, if we take any other point, for example, this one, there will be many paths that will be shared between this point A and this point B, right. From the clock source to points A and B, there will be many paths which will be shared, and therefore, their delay will get correlated, and therefore, the impact of process induced variation is expected to come down. So, it ensures, the mesh architecture ensures more paths between mesh drivers and clock sinks, and therefore, very small skew is observed, and decreased impact of process induced variation is also observed in this kind of architecture. And it is also robust in the sense that if it is a mesh architecture, then even if one links get broken, the clock can reach through other paths, right, and therefore, this architecture is more robust than a tree kind of architecture. But what are disadvantages of mesh architecture? So, the first disadvantage is that it will have more capacitance because of more wires being used in the network, right, and it will lead to increased power consumption because of increased capacitance, right. Remember that dynamic power is proportional to capacitance being driven, and therefore the mesh architecture will consume more power. Another reason for more power being dissipated in a mesh architecture is because of short circuit power dissipation. Now, in this case we can think that this driver A and driver B, right, these two are driving the same points, in the sense their output of two inverters are being shorted, right. Now, if these inputs have some skew, slight skew in input because of, say, process induced variation in these path, right, and because of a small skew, what can happen is that the one input is 1 and the other input can be 0, right, and therefore, for a short duration there can be a short circuit path between the power and the ground through the NMOS and PMOS internal to these inverters, and therefore, short circuit power dissipation can be higher in mesh architecture. So, we should be careful about the short circuit power dissipation also in the mesh architecture of clock distribution network. Now, let us look into a concept which is known as useful skews. Till now what we discussed is that the clock tree synthesis tries to minimize the skews, right. Ideally it should be 0, right, but in some situations useful skews can actually help us improve the system performance. So, introducing well controlled skews can improve the system performance, and when that happens, then those skews are known as useful skews, right. Now, when can clock skews be useful? It can be useful if there is a significant difference in the slack on the two sides of the flip flops. So, we will see an example, then it will become more clear. So, if there is more on the two sides of flip flop there is a significant difference in slack, then what can be done is that we skew the clock signal at the two different endpoints or different start and launch and capture points, and as a result what happens is that we will be able to allocate excess margin on one side of the flip flop to the more critical side, right. How it can be done, we will see with an example, then it will become more clear. Because it helps if we do some clock skewing, then what we are basically doing is that we are providing more time for data to propagate on the critical path by changing the clock's skew, right. Now, how it can be done, let us see with the help of an example. Suppose this is a portion of circuit that is or the portion of circuit that is critical, which is shown here, right. Assume that our flip flops are ideal, because assume that the setup time of these flip flops are 0 and clock to Q delay is also 0, right. Let us assume that, and let us assume that this input delay is very small at this point, and therefore, this path is not critical. Similarly, the output delay is small, and therefore, this path is also not critical, right. So, the critical portion of our design is the central, this part, right. Now, if we look into this flip flop FF2, it has got two paths, right. First path is this one, in which FF2 is basically the capture flip flop, and the second path is basically this one, in which FF2 is the launch flip flop, right. Now, in this in this circuit, what we have done is that the clock skew has been made 0, the ideal condition. The delay for all the clock pins is 50 time units. Let us assume that the time units given here is in picosecond, right. So, we have 50 picosecond delay on all the clock paths, right. So, therefore, since the delay are same everywhere, where clock skew is basically 0, right. Now, let us consider or evaluate that at what maximum clock frequency this circuit can operate, right. So, there are two paths. First, let us consider this path in which FF2 is working as the capture flip flop, right. So, in this case, if FF2 is the capture flip flop, the arrival time will be 50 plus 200, right, that is the arrival time. And what will be the required time? The clock period, we are considering setup analysis, right. So, setup constraints. So, T period and plus 50, 50 is the delay on the capture clock path, right. Now, we have assumed the clock to Q delay of flip flop is 0 and also the setup time of the flip flop FF2 is 0 for the sake of easy analysis, right. So, this is the constraint for the first path, right. So, we can simplify it, we can just cancel this out and we can say that T period should be greater than 200 picosecond. Now, let us look into the other path in which FF2 is working as the launch flip flop and FF3 is working as the capture flip flop. So, what is the arrival time? 50 plus 300, right, and required time similarly is T period plus 50, 50 is the clock is the delay of this part, right. So, we can write, if we can cancel out this 50, 50, we get T period should be greater than 300, right. So, we have two constraints, one constraint is coming for this path and the other is coming for this path, right. Now, one constraint is saying that T period should be greater than 200, the other is saying T period should be greater than 300. So, the most stricter should be considered, right. If we follow the stricter, then the lenient, that is T is greater than T period should be greater than 200 will automatically be fulfilled, right. So, the minimum value of T period can be 300, it should be at least more than 300, right. So, if that is the case, then we can compute the maximum clock frequency as 1 divided by 300 picosecond, that turns out to be 3.33 gigahertz, right. Now, this is the case when the skew was 0, the ideal case. Now, let us introduce some useful skew, right. So, what we did is that in this circuit we have introduced, instead of taking a 50 picosecond as the delay on the clock path, we have increased it to 100 picosecond, and on the other side also, on this path also we increased from 50 to 100, right. Now, let us compute the timing requirements for first for FF2 acting as capture and then FF3 acting as the capture, right. So, when FF2 is acting as the capture, the launch path is this, right. So, that the arrival time is 100 plus 200 and the T period it should be less than T period plus this is the delay on the capture side, capture clock path, right. That is what 50 is here, right. So, we can simplify it and write, say 50 goes on the other side, it becomes 250, right. So, 250, so T period should be greater than 250, that is the constraint for FF2 working as the capture flip flop. Now, what will be the case for FF3 acting as the capture, right? We can easily evaluate again. So, the arrival time will be 50 plus 300, right, and the required time will be T period plus 100, 100 is the delay on the capture clock path, right. So, from this what we get, we can take 100 to the other side and you can easily simplify, we can write T period is greater than 250, right. Now, in this case both these constraints are saying that T period should be greater than 250. So, what should be the minimum value of T period? It can be minimum is 250 and from that we can compute the maximum clock frequency that which this circuit can operate, right. So, we can get F max is equal to 1 divided by 250 picosecond is equal to 4 gigahertz, right. So, we have enhanced the maximum operable frequency of our circuit by introducing skews in our clock distribution network, right. So, what basically we have done is that by introducing extra delay on the path which was critical earlier, this path was critical, right. By introducing extra margin, extra delay on this clock path, we are allowing clock signal to propagate for a longer duration on the critical path, and as such we are getting some surplus slack which was observed on this side, we are utilizing it on the other side of the flip flop, right. Now, a couple of things are important to note here. The first thing is that we have increased the delay of say this clock delay element, this element from 50 to 100. What if we increase it further? If we increase it further, what will happen is that this FF2 will become more critical, right. Earlier the critical path was related to FF3, right, the path ending at FF3, or the when FF3 was acting as the critical FF3 was acting as the capture flip flop, right. If we make this delay element larger than 100, then the FF2 path ending on FF2, that will become critical, right, and therefore there is some optimum value of the clock of the delay in the clock network that will give us the maximum operable clock frequency, right. So, we need to, so the tool which is trying to introduce this useful skew need to come up with an optimum value, right. It is not that we can just add delay element and it will lead to improvement, right. Another important thing is that when we introduce delay on the clock path, right, for example, this clock path, we are improving the setup requirement, or we are improving the or relaxing the setup constraints or setup requirement, but we are making the hold requirement more stricter, right. For example, if we are add from 50 to 100, if we are increasing the delay of this circuit element, right, then the clock is reaching the capture flip flop later, right, and therefore FF3 is more likely to have hold violation than earlier, right. So, there is, while reducing the or improving the setup requirement of our circuit or improving the maximum operable frequency of our circuit, we should be careful that the hold violation does not get introduced because of clock skewing. So, the CTS tools calculates useful skew targets for all critical registers, and then it increases the arrival time of the clock for target registers by adding of delay buffers or extra wires. And use another side effect of introducing skew in the clock distribution network is that it helps us decrease the problem of voltage drop, right. So, in the earlier lecture when we discussed chip planning, we discussed that there is there can be problem in power VDD voltage dropping when it reaches the standard cells, right. Now, if we skew the clock the clock signal, what happens is that the flip flops get triggered at different time interval, all of them do not get triggered at the same time, and therefore, the activity of the clock of the signal that was there in the circuit earlier, which was occurring concurrently, that gets skewed over the time, and therefore, the simultaneous current drawn from the power supply, that can be reduced, and therefore, the voltage drop problem can be reduced by introducing the useful skew, right. Now, after we have done the clock tree synthesis, then what happens is that the clock network has been built, and now we have got a realistic clock network. Before clock tree synthesis, our clocks were ideal. That was the assumption we made in synthesis. We added some constraints like latency, uncertainty to model as some effect of realistic clock, right, by using some estimates, right, but those were very crude measures. But once we have built the CTS, then we can actually compute the delay of the circuit elements in the clock network, and based on that we can do the timing analysis, right. So, now the timing analysis that will be done, it will be more realistic because the clock network has already been built and actual delays on the clock path can be accounted for. And therefore, what can happen is that once we do CTS, new violations can come up, right. And to do the timing analysis, we also need to instruct to the static timing analysis tool that now the clock tree synthesis has been done, use the propagated delays of the clock signal rather than the set clock latency and the network latency and source latency that were used earlier, right. So, source latency can still be there in our SDC file, but the network latency that was earlier introduced before CTS and during synthesis, that needs to be removed, and use, instead of the network latency, we should use the actual value of the delays of the clock of the circuit elements which are there in the clock network, and to instruct the STA tool that use the realistic delay, we use a command set underscore propagated clock in the SDC file, and we can give all clocks if all the clocks have been built. Right. Now, new timing violations may show up after CTS, then we need to fix it due to, and why these new timing violations can come, because of the additional skew that we will see now because of the realistic clock network, and also because some logic components on the data path, they might be displaced, right, to make some space for the clock buffers and the structures needed for the clock tree. So, some circuit elements might be moved from the circuit elements which were on the data paths, those might have been moved away from their respective position, and therefore, the delay of the data path might have increased, and therefore, the new timing violations can come up, and and the CTS tool needs to fix those timing violations. Now, once those timing violations are fixed, maybe using some optimization techniques like resizing or making incremental changes in the placement and so on, then the clock network is frozen, meaning that we have done the inserted all the circuit elements on the clock path, we have done the routing also of the clock signal on the clock path, and therefore, we say that our clock network is fully built, and then we do not allow any change to happen on the clock network unless and until it is a very important change. Without changing that, we cannot move ahead, and those changes are very well controlled and are used and are introduced in our design using ECO or engineering change order. Otherwise, after CTS is done, our clock network is completely built and it is frozen, right. So, if you want to know more about the topics we discussed in this lecture, you can look into this book. Now, to summarize, in this lecture, what we have done is that we have looked into clock tree synthesis, right. We looked into various types of clock distribution network and also clock network architecture, and we also looked into the concept of useful skews. In the next lecture, we will be looking into the routing of a design. Thank you very much.